state of the system. So the state is a kind of a description that gives you maximal information. Maximal information, not in the sense that everything that happens is included, because in my model of the cars in the city, I'm, for example, not caring who is driving the car. I'm not caring what color the car is. I'm not caring whether the car is accelerating or slowing down at this moment. My model at this moment only has the position of the car and the speed of the car. Why do I limit myself to those things? Because these are the things that I have decided as a modeler are the important things. I want to know where cars will be at some future moment. In order to know that, I need to know at this moment where each car is and what speed it is driving in which direction. That's what I need to know. So the state, ideally, is the minimal description that gives you all the information you need in order to derive what will happen next. So the state is what will tell you how things will change. Now, there are some interesting philosophical or epistemological aspects about that. That is that when a physicist speaks about the state of a system, the physicist would tend to assume that everything is included in that state. Physicists typically don't model cars in cities, they model particles in electromagnetic fields, let's say. When a physicist models an electron in an electromagnetic field, the physicist will assume that the state of the electron is all there is to know. Now, that is a highly idealized and highly specific assumption. Most models are not like that. Most models, we simply can't know all the details. We don't know everything there is to know about the car or about whatever we are modeling. So most models are highly simplified. The state, in principle, gives you complete information, but complete information relative to what you're trying to do. Relative to what you're trying to do to predict the traffic, the color of the car or the driver of the car or how many people are in the car is irrelevant. On the other hand, if you're a physicist who speaks about the universe, you're trying to make a state function that describes the whole universe, and you kind of assume that everything there is to know is present in that state. That's a metaphysical assumption. I would say that in practice will never work. So in practice, the state is complete information relative to what you're trying to do and relative to what you can do. Because you might like to know maybe what the psychological state is of the driver of the car, because that might give you a better idea of whether that car is likely to quickly go to the orange light or stop. But you know you will never get that information for all the drivers of all the cars, so in your model you're ignoring that. So let's go a little bit more in detail. I'll take my example of this brilliant table. So that is my very simple system. There are two balls. And suppose that I have just two properties, left, right, up, down. Now I could describe the system as ball 1 being left, up, ball 2 being right, down. That's my state of the system. That's, in this very simplified model, is a complete state of the system. Of course, if you want to predict how the balls will move, you will want to be a little bit more precise than left. You will want to say, for example, that the ball is at position x1 and position y1, and this other ball is at position x2 and y2. So the simplest version left up, the more precise version, x1, y1, which are your coordinates, which you can measure in pencil. So that's the state of the system. If you want to predict where the balls will move, you will typically also want to know what is the speed and the direction in which that ball is moving. If you know the speed and the direction in which that ball is moving, you will be able to predict where the ball will be at a later moment. So now we come to this core concept of the state space. So a state is the most complete description of the properties of your object at a particular moment. The state space is the set of all possible states in which the system could be. So in this case, the state space is not just this x1 and this y1, it's all the ranges of x, which may go, for example, between 0 and big X, and here they go between 0 and big Y. So all the values in between there and all the values in between there are part of my state space. So in this case, my state space is all the possible values x1, y1 for the first ball, all possible values x2, y2 for the second ball. That means that my state space here is 4-dimensional. 2 dimensions for one ball, 2 more dimensions for the other ball. Each of the properties, when it's variable, it defines a dimension, or what's also called in science a degree of freedom. Why do we call it a degree of freedom? Because the ball has the freedom to move left, right, or to move up, down. It has 2 degrees of freedom. It can move in this direction, it can move in that direction. That ball can also move in both directions. So together the balls have 4 degrees of freedom. So the state space is then the space of all the possible states. And let's make a very simple example of a state space. Do I have a sponge somewhere? Let's make it a little bit more complicated than left, right, up, down. Let's speak about left, right, bottom, top, no, back, in front, behind, and above, below. So these are my binary properties. Left, right is one binary property. In front, behind, and above, below. So I assume in this case that I have a system with one object that can have one of each of these versions. So what is my state space? It's the collection of all the possible states in which this object could be. So that object could be left, in front, above. It could be left, in front, below. It could be right, no, it could be left, behind, below, etc. There are 8 possible combinations. 2 times 2 times 2. 2 times 2 is 4, 2 times 4 is 8. There are 8 possible combinations. That means my state space has 8 states. It's of course an extremely simple case. Inside you will very rarely have examples like that, but it's just to show you how the state space is built. It is built by taking the number of possibilities for one property, multiplying by the number of possibilities for the other property, multiplying by the number of possibilities for the next property, and so on. So if one property has, let's say, n1 possibilities, and the other property has n2 possibilities, you multiply them. If a third property has n3 possibilities, you multiply each time the number of possibilities for each of the properties. Now what happens if you have different objects? Suppose you have an object A, which has n A1 possibilities, and A2 possibilities, etc. And then you do the same for object B and B1 times and B2. That means each time you add either a property or an object, you have to multiply. The number of possibilities expands each time you add either a property or an object. That means each time you're adding degrees of freedom. You're giving the system more space, more possibilities to be in different states. So your state space will very quickly become very big. So state spaces typically are enormous spaces. They are typically infinite because most of the time we choose properties like this y1 that have an infinite number of values, but they are big not only in absolute numbers, they're also big in the number of degrees of freedom. Because if you add more objects, if you add more properties, you get more possibilities. So that principle that you multiply each time you add something, it can be described in the following way. If your state space is called S is a set of a number of states. Let's call them S1, S2, S3, etc. And then you want to add another state space. Let's say that this is the state space of object A. If you want to have a total state space, you multiply the state spaces. Now, how do you multiply state spaces? That's a construction in mathematics called the Cartesian product. The Cartesian product is a set that is made by taking one element from the one state space, one element from the other set, and each time making all the combinations. So that one is a collection of so-called couples, one from the A, one from the B, and then you take all possible couples where you combine one element from this with one element from that. Yeah.
Is there a way to add it onto this type of formulation if I don't want the objects to ever intersect? Because if I'm modeling something like billiard balls, logically they could never be in the exact same position. So is there a way to exclude all?
Then we get into a more complicated case. Then we come to the notion of constraint, which we will discuss later. But it's true that usually with these kind of models, you assume that your billiard balls are infinitely small. That means that they can be practically in the same space. I mean, it's an interesting case if you are, for example, making a model of the traffic in the city. At some moment, it may be that you make a computer simulation of all the cars. At some moments, one car is in the same position as another car. Of course, with real cars, that's not possible. But yeah, it may be easier to model if you kind of assume that they could be in the same place. So it's a good remark, but it's typically one of these kind of things that in first instance, when you make a model, you kind of simplify by assuming that they can be at the same place. So we see that whatever system you describe, from the moment you distinguish objects that can have more than one value of their properties, they have a state space, and that state space immediately gets very big. Now, I have defined the state space initially as just a set. It means a collection of possible states in which it can be. Now, why do we call it the space? Because it's not just a collection of states. There is also something like a geometry in that space. And in the simplest case, it means there is a distance. Some states are farther apart, some states are closer together. Let's say the simplest case, when you have binary distinctions, intuitively you would say this state and this state, they only differ in one thing. So distance one. But if now I take the state right behind below, and I compare it with this state, there are three differences. So I can say this state has distance one, this state has distance three. So this the general idea. The distance becomes bigger the more steps you need to do if you want to go from the one to the other. If I want to go from left in front above, I need to change three things before I get to this state right behind below. So that's the general idea. It's the same as with a billiard ball. If I want to move this ball to there, I will need to go to the right, and I will need to go down. So I will need to make a bigger distance than if I just want to go here. So typically state spaces have a so-called distance metric. A metric is a mathematical term to say that between two states, let's say S1 and S2, you can give a number, distance is d, for example. There is a particular number that you can put whenever you have two states. Now, what's the use of the distance metric? Because typically when the system is evolving, it's changing from one state to another, the bigger the distance, the longer it will take to go from the one to the other. Let's take an example from evolution. We could, for example, compare the genome of different animals and start counting the genes. The genes have so-called base pairs, so you can in principle count for each gene what of the four possible bases it is. So you could describe a genome as one long string of things which each time has a property with four possible values. So you could in principle have an enormous state space of all possible genomes. And then you can start calculating distances between one genome and another genome. Why could that, for example, be interesting? Well, you could, for example, compare the genome of a human with the genome of a chimpanzee and notice that, for example, I think it's something like 99% the same genome, but the percentage is not that interesting. What you really want to know is how much time would it take to get from the genome from a chimpanzee to a human? Because then you're thinking in terms of evolution. Now, humans have not evolved from chimpanzees. Humans and chimpanzees have both evolved from a common ancestor. So what you might do is, if you compare the genomes from a human and the genome of a chimpanzee, you might try to estimate how much time would it need if I start from a common ancestor for those two to separate. And there are estimates of how quickly a genome changes, how often a mutation arises, and like that you can calculate what is the likely time that has passed since humans and chimpanzees had a common ancestor, and then typically they find about 7 million years ago. So that's one of the examples of how you can use this distance metric in the state space. Now, most distance metrics are not counting the number of differences, they are using the more traditional formula, which some of you may have seen. That is that if you have a distance in three dimensions, x, y, z, you will have this kind of formula: x1 minus x2 square plus y1 minus y2 square plus z1 minus z2 square and the square root of all that. That's a typical so-called Euclidean distance metric. It's a distance metric that works in three-dimensional space. If you want to know how far this spot from this spot is, you measure the x, y, z coordinates, you put it in that formula, then you will know what's exactly the distance. So there is more than one distance metric. Depending on your state space, there may be other versions. Another example where that could be useful, comparing texts. A text you get on the internet can in principle be analyzed as the state of some potential text. You could, for example, say, each word in my dictionary, I count how many times it appears in the text. So each word defines a property. The number of times the word appears defines a number for each property. And then I could, in principle, calculate the distance between two texts by seeing how many of the words are the same, how many times do the same words occur. That's a little bit too simplistic, but there are formulas like that that calculate kind of similarities between texts in this way. And that makes it easy. For example, if you find a text on the internet that you find interesting, that algorithm could find you similar texts. I suppose it could, for example, also be interesting if you want to check whether there is plagiarism, for example. That could be another way of finding the two texts are similar. So these methods, they are used in lots of different domains. But I want you to understand the basics. I don't want you to remember the formulas. And now we finally come to what I think is one of the most important concepts here, the concept of a dynamic system. So I assume that I have a system. The system has a state space. At a particular moment in time, I know what state the system has. So at time t, the system is in state S of t. What I now would like to know is what's going to happen in the future. I want to be able to predict, like in the case of my billiard balls, if this ball is here moving in that direction, where will it be in half a second? Or if I have my simulation of the traffic in the city, I know at a certain moment the positions of all the cars and the speeds of all the cars. I would like to know, let's say, whether in half an hour there will be a traffic jam. So from S of t, I want to know of S of t plus 1, let's say plus 1 step forward in my simulation. Now, the typical way this is done in science, but which I'm not going to explain, is that you use a differentiation. ds over dt is some function of s of t. That's a so-called differential equation. What it says is the variation of s over t is a particular function. I'm here going to use a simpler formulation and say that s of t, or rather s of t plus 1 is s of t plus some function. That function, that is the dynamics of the system. Dynamics is the part in physics that describes how things are moved forward. What is it that makes things change? In simple things like billiard balls, dynamics depends on the forces. The force, if I give a hit to that ball, the force is what will determine where the ball will end up. But generally speaking, there is some function, a function of the state and of the time, and that function will tell me what the next state will be. And then if I know that function, I can calculate. And if here I put the state, and here I put time, and I know, for example, that at time t, my state is, let's call it S0, and then I calculated t plus 1, and I find that it is state S1. I can do that for all the states, for all the times. What do I find? I find a line. This line is called the trajectory of the system. Imagine, for example, that you're describing the movement of a cannonball. The cannonball shoots up and then goes down under the effect of gravity. It will describe a trajectory to space. This is a generalization of this notion. It's a trajectory not to physical space, but to state space. In the simplest case, the state space is the physical space. In most cases, the state space is much more complex than the physical space because it has many more degrees of freedom. But it's a generalization. Trajectory is the movement that the system will describe to its space of potential states. And the assumption here is that the trajectory is well defined. Yes.
Is this still useful in social analysis, or is it too complex?
It depends for your social analysis what you are measuring. A very simple case in which social analysis in which this is useful is, for example, estimates of population numbers. You have already seen these population numbers, like saying, this is the population now in 2020, this will be the population 2050, and you can describe a trajectory. It all depends on what you're measuring. Some things are pretty predictable, like the number of people that will be alive. Other things will be less predictable. Economists try to make predictions of that, but economists are notoriously bad in their predictions. Usually their predictions are kind of valid, like maybe for half a year or maybe for 2 years, but don't count on them too well. But still they're trying. And it's good that they try, because if the predictions are correct, it gives the politicians an idea of what they should do. If, for example, the economists calculate that unemployment will increase more than a certain amount if a particular measure is taken, well, you would like to know that, and you would say maybe we should do something to counter, to compensate for that increase in unemployment. But so the assumption here is that the trajectory is specified, and as we will see later in the course, that's an assumption which for most complex systems you can't really make. But if you make that simplified assumption that you can calculate the trajectory, you can derive all kinds of interesting things from that. Yeah.
Would it be way easier to derive the trajectory if we would have a planned economy? As in, we would see the error within our predictions, and thus we would be able to refit our function of the trajectory through time while we are using it. It would be a way better way of quantizing the whole of the economy.
Well, the planned economy, in principle, in the Soviet Union, they were using these kind of methods to plan, but in practice it didn't work very well. So whether it's planned or whether it's a free market economy, the economy is too complex as a system to allow this kind of precise trajectory. But still, as I say, the closer you come to the real trajectory, the better. So it's good to continue trying, and maybe you will learn some lessons so that next time your predictions will be better.
We would have more degrees of freedom, so our predictions would be closer to the truth, simply mathematically.
No. More degrees of freedom precisely means that it's more difficult to predict.
Yes, but you can refit your function and keep on refitting it like a Taylor series.
That's what scientists are doing. They're trying to refit the function to the data, but the fact that it fits your past data is no guarantee that it will fit your future data. But that's one of the methods that you use indeed, is look at what has happened up to now, try to fit a curve that goes to your data, and then extrapolate the curve to the future. Sometimes it works, most of the time it doesn't work too well. It all depends on your system. If your system is simple, if you send a rocket to Mars, you know with what speed the rocket leaves the Earth atmosphere, you know the gravitation of the Sun and Mars, you can calculate exactly when the rocket will arrive in Mars. Simple physics. Try to do the same for the unemployment rate in an economy, probably won't work. But it's the same principle. Okay, let's have a 10-minute break here.
Hello. How are you? Hey, how are you? I had a good yeah, I
For sure. Yeah, exactly. Because it's such a big, because that's what I would think happened to plan economy. Because we would have, we would see the populations way better. Exactly. That need to be disturbed.
yeah. Can be nice, but it's not me. And the program was good, the films. You got the wall, I heard. No,
So for scarcity, we're not worried. For all the rest of the economy.
They have varieties, and the Chinese also have varieties. The Chinese have switched to a free market.
Yeah.
And if the Chinese do it and closing up.
Only about communities, like, do you know how to get next weekend? Only about travel. So the pictures are nicer than that.
That's how it's done.
He's very. I'd pass.
And then after an hour, you'll have given us the first thing. And like, thank you for this. You know, the question from Space Moon to the community.
So this is the depiction of a trajectory starting from a particular state at 0, and it shows how the state changes over time. Now imagine that I would be able to calculate that not for this particular state, but for any state. So suppose that my state space would be two-dimensional, and for every state, I could know where it will go. If it's here, it will go there. 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 And I pick everywhere in my state space, I draw arrows where the arrow shows what the next state will be. This is a very interesting representation, which is called a phase portrait of the system. And here you see a simulation. All these arrows are what the system will do if it comes in one of these states. And there you see the blue and the red. If it starts there from top, it will follow the arrows. If it starts from here, it will circle. That's a very interesting notion, that is that if you draw all the arrows, you can see that sometimes the arrows all go to the same spots and they stay there. And that is the notion of an attractor. Let's look again at our billiard table. Let's assume that the billiard table is not flat, but that there is kind of a depression in the middle. Well, in the middle there's a depression, then you know that that ball will go to the middle, that ball will go to the middle, and any ball that would be here would go to the middle, and they would all end up in this depression. That kind of a depression, it's a part of the state space that is called an attractor. Now, attractor is one of the most useful concepts in complex systems theory. Because an attractor is a very simple, intuitive concept, but that still teaches you a lot about the system. If the dynamical system has an attractor, and typically it will have more than one attractor, then you can predict that wherever you start in the state space, in the neighborhood of the attractor, you will end up in the attractor. It's like that billiard table with a bump. If you know that the ball is somewhere near the bump, it will end up at the bottom of the hole. It will end up at the bottom. Now, if there is more than one bump, then you don't know a priori which one it will be, but it will depend on your state space. Let's assume that there are two attractors. Then you can draw the boundary and say, everything in this corner will end up here, everything in this corner will end up in that attractor. So this is what the phase portrait tells you. In this case, we see that there is a kind of an attractor in the middle where it always stays in, it rotates there, and there is on the outside, it continues moving. But it can have all kind of complicated geometries. But what you need to remember is there are zones that the system can enter, but once it's in there, it cannot leave it. And these zones are the attractors. And the surrounding zones, that means the zones from which you end up in the attractor, are called the basin of the attractor. Basin, it's a little bit like a water basin. Imagine a hilly landscape with mountains, and there are lakes. The attractors are like the lakes. The water basin is the region, the valley, from which all the water will end up in a particular lake. So the lake is like the attractor. The basin is the region from which everything will end up in the attractor. So we will see later in the course, we will see more applications of this attractor concept, but it's an extremely simple, intuitive concept that can explain a lot of things. Because whatever your complex system is, usually you cannot calculate that trajectory. But you generally have an idea of the state space, and you have an idea of certain attractors in the state space, and then it's sufficient to know, am I on this basin or am I in this basin? If I'm in this basin, I will end up in this attractor. If I'm in this basin, I will end up in this attractor. I don't need to know all the details. Like here, it's exactly calculated, but you don't need to know all the details. What you need to know is where are the attractors, where are the basins. So that makes this concept of an attractor a very useful, intuitive concept to understand complex systems. That brings me to my next chapter on information and entropy. Now, these two concepts, information and entropy, are about the most important quantitative concepts in the description of complex systems. I mean, we all have an idea of what information is, but it's good to know the mathematical definition and also to know the definition of entropy, which is a term that most of you will have heard, but few people understand well what entropy means. So we need to explain what it is. Also because entropy will lead to the definition of information. Information, actually, you can only understand after you have understood entropy. So these are two very basic concepts, but they are often misunderstood. And because they are misunderstood, I will not immediately start explaining entropy or information. I will start with simpler notions, notions that few scientists use, because they're so simple that they're almost trivial, but they will make it more understandable, the notion of variety and constraint. And I want to make another remark here, that is that information, it has become such an ubiquitous term that a number of scientists are starting to say, well, the universe is made out of matter, energy, and information, as if these are three basic substances. But that's a misleading concept, because information is different from matter or energy. Matter and energy are what in physics we call, they satisfy conservation laws. You cannot destroy matter, you cannot destroy energy, you cannot create energy, you cannot create matter, you can at most change the one into the other. If necessary, you can turn matter into energy or energy into matter. That's very difficult, but the total amount of matter and energy in the universe is fixed. You can't change anything about it. Information is not like that. Information is something that can appear and that can disappear. Very simply, I don't know something, I read about it, now the information has entered my brain. There was no information there, now there is. But then I forget it, the information is no longer there, it has disappeared. So information is something that can be created and that can be lost. That's completely different from matter and energy. So information is not a substance. As we will see, information is something relational. We need to speak in terms of distinctions and connections to be able to understand what information is. So let me start with this very simple notion of variety. I just introduced the notion of a state space. The state space gives you the range of possibilities, of possible states that the system may be in. And of course, it's good to know how large is that space, how many possible states are there. Well, variety, simply put, is a measure for the size of the state space. A system with a lot of variety means a system that can be in many different states. Very simple, but we had this problem of what I call the multiplication. Whenever you add something to your state space, you have to multiply the number of possibilities, which means that you immediately get these enormous astronomical numbers. Now, there's a simple trick to reduce the number, to take the logarithm. So if n is the number of states in my state space, I will define the variety as the logarithm of n, and the logarithm to the basis 2. Logarithm to the basis 2, it's because we want to express things in a binary way, like, bits, binary digits. That's what we use in computers and information. It's kind of the simplest possible representation. So the reason we use logarithms in the binary form is because it will reduce everything to bits. So all the things we will be measuring, variety, constraint, entropy, information, we will all measure in bits. A bit means a choice between two options. So let's say the minimal variety is one distinction, which you have two options. It's either here or there. That has variety 2 states. In this case, n is 2. And logarithm of 2 is 1. So number of states 2, variety 1. 1 bit. Another reason we use logarithms is because logarithms have this nice property that the logarithm of a product, A times B, is equal to the sum of the logarithms, logarithm of A plus logarithm of B. Which means if I have state spaces and I add an object instead of having to multiply the number of states, I can just add the variety. So the reason we will explain variety in terms of logarithms is it makes the numbers easier, it makes the numbers smaller, it makes it easier to manipulate, we can add things, and we can express everything in terms of bits, which is kind of the natural unit of information, entropy, etc. Now, how do we interpret that variety? Well, it is the freedom of the system, the number of possibilities that it has. A system with more properties, with more objects, has more variety. It can be in more different states. So I said that variety, because it's a logarithm, allows me to add it, which means if I now make a system consisting of different objects, for example, suppose that I have that A, or let's say that I have a system consisting of a ball and a cube, a billiard cube, then the variety of that total system will be the variety of the ball plus the variety of the cube. If I add objects or if I add properties, I just need to add the variety. So variety tells you the freedom, the range of possibilities. Now we come to the opposite concept of constraint. Constraint is what reduces my variety. Constraint means that the system cannot use all its possibilities. There is an original variety, and then I reduce that variety. You can take my billiard ball example. I have one ball, that's the state space. The ball can be in any position here. And now I do something, I put a break in the middle of my billiard ball. What have I done? I have reduced the state space. I have cut it in two. The ball is on the left. The ball can no longer move to the right. The number of states has decreased. The variety has decreased. The variety, let's say that these are all the states. I have cut the variety in two. That means I have reduced my variety with 1 bit. 2 is the distinction, a binary digit. That is a constraint. So what is the definition of constraint? C is the maximum variety. It means without a constraint minus the actual variety. I start with what is theoretically possible, all the possible states. That's my maximum variety. And then I notice that there is something, in this case it's a blank, that stops the system from moving in its whole state space. Something constrains the system to remain within a small part of its state space. That's what constraint is. Constraint is a confinement, a reduction, a limitation of the state space, so that the system, you take away freedom from the system. The ball can no longer move to the right. Constraint is what takes away the freedom, what reduces the number of possibilities. So in this case, the constraint is something very physical that you can imagine, but let's take a more abstract example. Imagine a very simple system with two binary properties. I'm looking at berries, and I can say that the berry can be either red or green, and either small or big. This is a system with 2 times 2 possible states. Let's just say it has state space n is 4, logarithm of n is 2 distinctions, 2 bits. That's my system. But now I look at my berries and I notice that whatever berry I consider, the berry is either red and big or green and small. There are no big green berries and there are no small red berries. Maybe just because the green berries are the unripe ones, they're not yet big. The red berries are the ripe ones, they are big. What does it mean that I started out with 4 possible combinations and I noticed that there are only 2 in reality? So my original was 2 bits. I noticed that there is actually only 1 bit. So my constraint is 1. 2 minus 1 is 1. So in this case, this state space has a constraint. So why is this interesting to know this constraint? The constraint gives me information. If I know that there is a constraint, I know that whatever berry I take, if it's red, it must be big. Imagine that I'm taking berries from a pack in the dark. I can't see which are the ripe red ones, but I feel that some of them are big and some of them are small. Well, I know because of the constraint. If it's small, it will be green, so it will not be ripe. If it's big, it must be red, so it will be ripe. So the constraint gives me some information. The constraint is what is reducing the state space, it's reducing the number of possibilities, and by reducing it, it's telling me more, it's giving me information. So that is, as we will see when we define information in more general term, it's a generalization of this idea. Information is that what reduces the range of possibilities. Yeah.
we call this also a symmetry between the red and the bigness of the object. Because if it is red, it is also big, like an object showing on the left and showing on the right.
A symmetry is a kind of a constraint, but not all constraints are symmetries.
Hey, Francis, I have a quick question. It's a bit going back to the properties. But are the properties of the berry, for example, always only inherent in itself, or can they also be relational to the context? So you say it's binary because the berry is only red, green, small, and big, but can it also be fallen off the tree or hanging on the tree? So basically, the property in description to its environment.
Yeah, yeah. I spoke earlier about predicates with more than one position relations. Yes, the relationship could be it is to the left of the tree, or it is on the tree or below the tree.
So even if the object in itself or the system is binary, in its context, it's maybe not.
No, no. It depends what you include. If you include the context as defining one of the properties, yes, it can be the relationship to the context that defines another property. Of course. Okay, so now we have this insane simple concept of variety, the number of possibilities, constant that reduces the number of possibilities. Now we're going to generalize it to this notorious concept of entropy and information. So I have to again write a formula, and it's a bit of a complicated formula, but it's a very fundamental formula. That's why I will write it down. I still won't ask you the formula for entropy. Conventionally written H. H is minus sum over all the states of the probability of the state times the logarithm of that probability. So that's not an intuitive formula. I don't expect you to understand it from the formula of. So what we will do is we will look at the special cases of that formula. So first, why do I use a probability? Because in some cases I simply don't know exactly what state the system is. I can say, well, there's a certain probability that it's here, and there's another probability that it's there. So it's a kind of a generalization. If I don't know exactly what state the system can be in, I can just say it's more or less probable to be here or to be there. What does that formula mean? Well, let's take the first case. Probability is 1 for one case. For example, I know that the system is in state S1, probability of S1 is 1, which means that the probability of any other state that is not S0 is 0. So here I have reduced it to the case where I know the system is in state S0 and it can't be in any of the other states. Now I can calculate what the formula is. So I need to have the sum of the probabilities. So there is a 1 there, minus 1 times the logarithm of 1, minus 0 times logarithm of 0, and the same for all the others. So I can start by saying 0, I forgot about it. I get minus 1 times the logarithm of 1. So the logarithm of 1 is actually 0. So what do I find is that my entropy is 0. In the case that I know exactly what the state of the system is, my entropy is 0. So entropy is a generalization of variety. Variety means there is a wide range of state the system could be in. When that variety is reduced to just there is only one, then the conclusion is variety is 0, entropy is 0. Yeah.
Do you just mean that if your state is homogenic, there's no entropy?
Not homogenic, there is one state. It means you know what the state is. So we're speaking about your knowledge about the state. You know it is in that state. Yes?
I'm sorry, where did that first logarithm come from? We have one logarithm on that version of the formula and two on that.
Well, it's probability times logarithm probability. So 1 times log 1,
okay.
0
All
times
right,
log
fine.
0.
Thank you.
If you know exactly in what state the system is, it means the system has no freedom to take any other state. There is no uncertainty. You know exactly what the state of the system is. So 0 entropy means 0 uncertainty. So entropy in this formula, there's another form of entropy that we will discuss later, is equivalent to uncertainty. 0 uncertainty means you know exactly what the state is. So let's look at the other extreme. The other extreme is it can be in any state. You have no idea what state it could be. Any state is as good as any other state. That means that the probabilities of all these states are the same. Let's assume that there are k states. Then the probability of some state is equal to 1 over k. Well, it must be in one of the k states. I have no reason to assume that one state would be more or less probable than the other one. So all the states have probability 1 over k. Now, if I plug that into the same formula, what I get is the sum over k of 1 over k times the logarithm of 1 over k. Sum over k, that means that's k times this. So I can take that away and I get minus the logarithm of 1 over k is equal to the logarithm of k. So the maximum value of my entropy is the logarithm of k, where k is the number of states. Now, previously I defined the variety as the logarithm of the number of states. Yeah. Maybe I should have used 10 instead of k. What I find is that my entropy is equal to the variety. So minimum entropy means 0, maximum entropy means it's equivalent to the variety. Now it's the intermediate cases that are interesting. What if the entropy is in between? So let's try to visualize that. So my first case was if this is a probability, and here are all the states. There is a particular state as 0 and has maximum probability. Probability 1. That was minimal entropy. Everything is 0 except this state as 0 has probability 1. My second case was this. All the states have exactly the same probability k. 1 over k. That's a sharp peak. That's completely flat. What now would be an intermediate case? An intermediate entropy would be one that is not completely flat and it's not completely peak. It would be something like this. That would be an intermediate entropy. And I have Here I have calculated two different entropies with the numbers that, yeah, so, well, these are two different probability distributions. So the dark gray one is more peaked, the light gray one is more flat. If I calculate the probabilities, the entropies of these two, I will find that the entropy of the dark one is smaller than the probability of the light ones. So what entropy measures is, you might say, the flatness of the distribution. The flatter it is, the bigger the entropy, the more peaked, the lower the entropy. So this peakiness means that the system is more concentrated in certain parts. The flatter it is, the more homogeneous, the more spread out the system is. Yeah.
So if I take 2 times exactly the same state, but one time my measurements become more accurate, the entropy lessens because my measurement was more accurate of the state. Or...
No, I mean, a less accurate measurement would be that you, for example, find that you don't know that it's here, but you know it's somewhere here. That would be a less accurate measurement. This would be a more accurate measurement. So the less accurate measurement would be one that has a wider range of possibilities. That's one where the entropy would be higher. So entropy is uncertainty. The wider the range, the more uncertainty is it this exactly, or is it this one, or is it this one? You have a probability distribution, and the flatter the probability distribution, the more the entropy. The narrower the probability distribution, the less entropy. Yeah.
So the uncertainty is not due to your not accurate measurement, but it's intrinsic to the state.
We make here the assumption that we only know the probability of the state. Why the probability? We don't say. Is it because you have made a bad measurement? Is it because you have only received partial information? I'm not specifying that. I'm just saying you have somehow a probability measure. If the probability is more flat, it will have high entropy. If it's more peaked, if it's more narrow, it will have low entropy. That's the only thing it says. But let's now go to the common interpretation in terms of disorder. Imagine that I try to describe those two systems in terms of probability. That are molecules that are randomly colliding. I can't say where these molecules are. The probabilities, they could be anywhere in this space. Here, they are all close together. That means here I know exactly where all the molecules are. That would have low entropy because I know where they are. That would have high entropy because they could be anywhere. So that's the idea. If those spread out more, the entropy will become even higher. The more they spread out, that means the larger the state space in which it could potentially be, the less I know. So that's the idea of this kind of thing, this kind of peak that's going wider or narrower. The narrower it is, the more I know where it is. The wider it is, the less I know where it is. And that's why when we speak about these kind of physical systems, we will say that this has a high entropy because I really can't say where the molecules are. They could be anywhere. Or this one has low entropy. I know exactly where the molecules are. So the fundamental interpretation of entropy is not disorder, it is uncertainty. High entropy means I'm highly uncertain of in what state the system is. Low entropy means I know pretty well where the system is. Zero entropy means I know exactly in which state the system is. So the interpretation disorder is kind of derived. It's not the fundamental definition of entropy. The fundamental definition of entropy is uncertainty. The less I know about where the system is, the less I know about in which state it is, the more the entropy.
So you could potentially know exactly where those are.
If you could potentially measure each of those individually, yes, then the entropy in that formula would be low. But yeah, in practice, of course, we assume that these are molecules, and I guess you can't measure all of these molecules. So you just have to know they are somewhere in the volume.
Is it then one particular moment in time, or because one system can be highly disordered and the next moment very ordered?
Well, that's what we will see in the next chapter. Then we will look at the dynamics. How will the entropy either increase or decrease? Because suppose that this is a gas. The gas is in a small box. I don't know where the molecules are exactly within the box, but I know they're all within the box. I open the box, the molecules escape, they go in all directions. The entropy has increased. There was entropy already in the small box, but when I open the box, the entropy becomes much bigger because the number of states increases. And that will be the interesting processes that we will discuss in later chapters. Why does the entropy sometimes increase and sometimes decrease? Because it can also decrease. But now that I have this definition of entropy, I can go on to my definition of information. Entropy was defined as uncertainty, which means actually lack of information. So what is information then? That's what decreases the uncertainty. So then I come to the definition of information. Let me make sure that I write the right formula. So what is the information? I assume that I receive information about something. It means before I was uncertain about the state of the system, and now my uncertainty has changed. The information is the reduction in uncertainty. Information means that I start with 1 degree of uncertainty, 1 degree of entropy. I get some information. The entropy after has diminished. Let's assume that the entropy after is 0. It means I have received information that I know exactly what the state of the system is. In that case, the information that I have received is exactly the entropy there was before I had received any information, and now I know for sure in what state the system is. My entropy is 0. So that gives me a formula where information equals entropy. But now imagine the opposite. Imagine that I was sure of the system. That means originally the entropy was 0. I knew exactly where the system was, and now I no longer am. Then I get that information is minus entropy. So that gives me the strange situation that sometimes some scientists will define entropy information as being entropy. Sometimes they will define it as minus the entropy. But actually what you need to do is it's before minus after. That is a very common confusion depending on which scientists you read. You may see that information is the same as entropy or it's the opposite of entropy, which is of course very confusing.
How can you receive negative information? How can it become?
You can receive negative information because you lose information. I gave the example of forgetting things. I had the information, I forget it. I have received negative information. That's the equivalent of erasing my information. Like I think on the blackboard, afterwards somebody erases the blackboard, the information has disappeared. You knew what the formula was, it was written there, somebody erases it, it's no longer there, you don't know anymore what the formula is. So the problems with information can be avoided if you always define information relative to a state of uncertainty. Your state of uncertainty can increase, you lose information, or it can decrease, you receive information. Yeah.
But when you forget something, you now know you forgot it. So is that a source of information again?
That's a tricky one. Well, maybe it's one very small bit of information you have. Like, I have known that, and now I no longer know it. It is one bit of
How do you
information.
like level which is, how do you say knowing that you forgot something is less information than the thing you forgot? How do you like differentiate the levels of how large the information is? Is it that
By the entropy measure.
Okay.
You need to make that calculation. Of course, that's all very idealistic. Nobody can make that calculation for things that you have in your memory. But yeah, theoretically, let's take an example. Let's say that I have a text. The text consists of characters. I know which characters there are, and then somehow the text gets garbled. Like, let's say, for example, somebody printed out a text on a piece of paper, dropped it in the mud, and now the text has become partly unreadable. That means I can still recognize some characters, but not others. I can, in principle, calculate of how many characters have become unreadable, or if there is a doubt, I can say this could be an A, but it could also be a B, but it certainly wouldn't be an X. In theory, you could apply that formula to say how much information have I lost by dropping that sheet of paper in the mud. Or vice versa, if somebody then cleans up the mud so that I can read it again, I can say how much information I have gained by that cleaning operation.
Right.
So now we can also understand these measures of information. Information typically is measured in bits at the lowest level, and then in bytes, kilobytes, megabytes, and gigabytes. And just as a reminder, a byte is 8 bits. That's a bit strange reason, but that's because in the old computers they used the ASCII alphabet for the different characters. All the letters plus numbers plus a number of marks plus capitals, small letters, all together was an alphabet of 256 characters, which corresponded to 8 bits. So that's why a byte would correspond to one character in the ASCII alphabet. 1 byte is 8 bits. And then you just go each time with more or less with powers of 1,000. 1 kilobyte is 1,000 byte, not exactly 1,000, it's 1,024 because we actually prefer to calculate in powers of 10, and 2 to the power of 10 is 1,024. And then from kilobyte you go to megabyte, from megabyte you go to gigabyte. Each time it's 1 power like that you add. So that's where this original definition of these measures come from. And then for some reason, when you measure the speed of an internet connection, you don't measure it in megabytes, you measure it in megabits per second. So that's a little bit kind of a historical reason why they use certain units. But all these units, in the end, are reducible to this bit that means the distinction 1, 0, yes, no, 2 different options. One last example that gives you maybe a little bit more of an idea why we use these logarithms. What you're trying to express here is that if you get an information, the more unexpected that information is, the more useful, the more informative it is. If somebody tells you something that you actually already kind of could guess, then you don't receive much information. And the example I give is, suppose that you reduce the weather forecast to 1 bit. Either it rains or it doesn't rain. That's the question is that most people want to know about the weather. Will it rain or will it not rain? But suppose that you get the weather forecast and you're living in the Sahara. So most of the time you wouldn't check the weather forecast because in the Sahara it practically never rains. So if somebody would tell you in the Sahara, well, the weather forecast says that it will be dry tomorrow, you would say, yeah, so what? I knew that. Well, you don't know 100% sure, but you're kind of knowing it. So suppose that we try to calculate how much information you would get if somebody tells you that it will or will not rain in the Sahara. Let's assume for simplicity that the probability of rain is 1%, 0.01 probability. Probability of dry is 99%, so 0.99. Now we can calculate the information you get from the weather forecast using that formula here, minus the logarithm of 0.01 times 0.01 minus 0.99 times the logarithm of 0.99. And I have calculated that in the lecture notes, and that gives you 0.08 bits. So under this assumption that the probability of rain is very small, the weather forecast in the Sahara will typically not give you much information. So that is where these probabilities come from. The probabilities say, if something is highly probable, then the uncertainty is small, entropy is small, therefore you already have information. So the additional information from the weather forecast is not that useful. But if we really want, we could split up that sum into two parts. The part of the information we would get if it does not rain, which would be very small, and the part you would get in the rare case that the weather forecast would be it will rain, and that will be much larger. I have calculated in the lecture notes. I mean, you don't need to know that, but it's a way to understand where the probabilities come from. If the weather forecast just confirms what the probability set will happen, 99% probability it will not rain, yeah.
So could you say that information is a difference that makes a difference?
Yeah. Okay, we'll have to leave or they will come and change the start.